Hi everyone, I'm Mohi Faden. Welcome back to the Solid Principles series. These are 5 super useful design principles that help us write cleaner, easier to maintain, and more scalable code. In the last video, we talked about the open-closed principle, how we can add new features without touching existing code. If you missed that one, definitely check it out. Today, we're moving on to the third principle, the Liskov Substitution Principle, or just LSP. Now that might sound a little technical at first, but it's actually pretty simple and powerful. LSP is all about making sure that when you use a subclass in place of a parent class, everything still works as expected, nothing breaks, and the behavior stays consistent. This principle is a big part of building code that's flexible, predictable, and solid. Alright, let's break it down. Here's the official definition of the Liskov Substitution Principle. Subtypes must be substitutable for their base types without altering the program's correctness. That's the core idea. Now let me explain that in plain English. It basically means this: if you have a class and then create a subclass from it, you should be able to use the subclass wherever the parent class is expected, and everything should still work just fine. In other words, subclasses shouldn't change the expected behavior of your code. They should just work, no surprising, no crashes. This is what keeps our code predictable, safe to extend, and much easier to maintain, especially when you're working in a team or on a big project. So, why does the Liskov substitution principle matter? Well, first, it helps keep your code consistent. When you swap a parent class with a subclass, the behavior should stay the same. That's what gives your code a solid foundation, no surprises. Next, it promotes predictability. You don't have to second guess if something weird will happen when using a subclass. That means fewer bugs and more confidence in your code. And finally, it makes your code more reliable and easier to maintain. When classes behave as expected, it's much easier to refactor or add new features later on. All of these benefits make LSP a must-known principle for writing clean, professional, and future-proof software. Let's bring this idea into the real world for a second. Imagine we have a transportation system. This is our base class. It simply calculates how long it takes to travel a certain distance. And the cool part, this system works no matter what kind of vehicle we're using. Let's say we're using a car. It's calculate the travel time using driving speed, pretty straightforward. Then we've got a bicycle. It moves slower, so the calculation takes that into account. And finally, an airplane. It flies much faster, so the system adjusts the time based on that. Even though each vehicle has its own speed, they can all be plugged into the same system, and the system keeps working just fine. That's exactly what the Liskov substitution principle is about. You can swap in any of these subclasses, the car, bike, or plane, and everything still works as expected. They all extend the same base system, but they handle their own logic internally without breaking the flow. Alright, now let's look at how things can go wrong when we don't follow the Liskov substitution principle. Let's say we're working on a bird simulation. Sounds fun, right? We start with the bird class, and of course we assume all birds can fly. But then we add a penguin. And here's the problem. Penguins are birds, but they can't fly. Let me show you what that looks like in code. Here's the code. We've got a bird class and it has a fly function that prints I can fly. Then we make a subclass called penguin. But since penguins can't fly, this class overrides the fly function and throws an error instead. Now check out this part. We have a function called letBirdFly. It takes a bird, any bird, and just calls fly. Everything works fine when we pass in a regular bird. But as soon as we pass in a penguin, the whole thing crashes. That's a clear violation of LSP. We tried to substitute a subclass, penguin, in place of bird, and it broke the behavior. This is exactly what LSP helps us avoid. Subclasses that look like they fit but act completely differently and break our system. Now, let's fix the problem and do the things the right way, the LSP way. We'll redesign the structure so that every class only gets the abilities it actually supports. Here's the improved version. We start with the basic bird class that just has a make sound function. Every bird can make a sound, even penguins. Then we create a new class called flying bird. It extends bird and now it gets a fly method. So only birds that can fly, like sparrows or eagles, would extend flying bird. And for birds like the penguin, we still extend bird, but now we gives it a swim method instead of forcing it to fly. Finally, we have a function called moveBird, and it only uses make sound, no assumption about flying. Now we can safely substitute any subclasses of bird, flying or non-flying, and nothing breaks. This is what the Liskov Substitution Principle is all about. Only give your classes the behaviors they actually support and don't force them into roles they can't play. Let's wrap this up with a few key benefits of following the Liskov Substitution Principle. First, it makes sure your subclasses behave in a predictable way. No surprises, no weird behavior. Everything works like you'd expect. Next, it helps you avoid bugs. When your subclasses follow the contract of the base class, you don't run into sudden crashes or edge cases. And finally, it makes your code easier to maintain and extend. You can add new features or classes with confidence, knowing the existing system won't break. By following LSP, you're writing code that's not only solid, but built to last. And that's it for the Liskov Substitution Principle. We looked at what LSP really means, why it matters, and how to design our code so that subclasses can safely replace their base classes without breaking anything. If you follow this principle, your code will be more reliable, easier to extend, and much less prone to weird bugs. I've also shared the full Python and Kotlin examples on GitHub. You can find the link in the description below if you want to check them out and play with the code yourself. If this video helped you understand LSP a little better, please give it a thumbs up and leave a comment if you have any question. And don't forget to subscribe, especially if you're excited for the next one. In the next video, we're going to explore the interface segregation principle, and it's going to be another fun one. Thanks for watching, and I'll see you there.